là học ở Đại học Khoa học Tự nhiên Thành phố Hồ Chí Minh khóa 2005. Sau đấy là Khoa có qua Mỹ, thì ban đầu là Khoa qua làm thạc sĩ với lại giáo sư Lê Dũng ở trường UT San Antonio trong vòng 2 năm. Tiếp sau nữa là Khoa có qua Đại học Kansas để làm tiến sĩ, và Khoa đổi hướng là từ phương trình đàm riêng qua làm xác suất thống kê, cực kỳ thú vị. Và bây giờ thì Khoa lại làm về stochastic PDE, nghĩa là kết hợp giữa giữa xác suất thống kê, giữa xác suất stochastic analysis với lại PD, và đây là một cái hướng rất là hot và trendy hiện nay. Mời Khoa.
Yeah. Vâng, cảm ơn anh Hưng. Cảm ơn mọi người đã cho phép Khoa give a talk today. So I'm gonna switch to English because there are some terminologies that I don't know how to translate into Vietnamese. Do you all see my screen?
Khoa thử Khoa cứ trình bày đi Khoa.
Okay. Yeah, so this is a stochastic heat equation with a distributional drift, and this is the paper is on arXiv, and this is a joint work with Siva Athaya in India, and Oleg Batkovsky in Weierstrass Institute in Berlin, and Leonid Mitnick in Technische in Haifa. So let me just tell you the equation first. So we are working on one-dimensional domain here, and this is the heat equation, and you have a space-time white noise and a drift. In stochastic analysis, we call this function is a drift. So it's just a function composed with the solution. So the aim of the project was to see under which condition, and we want the lowest regularity as possible, so that the equation is well posed. So namely, you have existence and uniqueness of a solution. So the class of drift that we look at here is distribution in Bezoff space, and this is the Bezoff space. So the beta is like the regularity index, and the Q is something like integrability index. And there's also a third index in the Bezoff scale, but we just take it to be infinity. So the initial data is about a measurable function. So some examples that we want to look at is the direct delta mass at 0. And in this case, people call it the skew stochastic heat equation, or any measure. Some more example is the principal value of 1 over u. This is also the same as the Cauchy principal value. And if you increase the power, you have a principal value of 1 over u cubic. So some of these cases, will make the equation. Our result cover the first two cases, and then the last cases here. In the community, we know that this has some weak solution, but our result doesn't cover. Okay. So let me tell you about the background. So we call this regularization by noise phenomena. So take, for example, a simple ODE like this, And because here the right hand side is not a Lipschitz function, so this ODE is ill-posed. You have starting from 0, infinitely many solutions. So these are 2 solutions, but the solution can stay at 0 as long as they want, and after a second they follow a curve like that. So you have infinitely many solutions starting from 0, but if we add a noise source, so here it is Brownian motion, then it is very well known that even if you start from 0, then this stochastic differential equation has a unique solution. So this kind of phenomena is called regularization by noise, where you introduce a noise source and into a ill-posed equation, then you get a well-posed equation. Okay, so there are many works on this kind of problems. So for ODE, so if there's no noise, so we know that only when B is Lipschitz, then there is a unique solution. And at most, if B is continuous, then you have existential solution. But for stochastic differential equation, when you add a Brownian motion on the right-hand side, then you have a unique solution when for any bounded measurable B. And this is known like 40 years ago now. So for integrable space and time, there's a very well-known result of Krylov and Rockner in 2005. So where they show that there is a unique solution under this condition. But probably people call it LPS condition, some fluid related. So for SPDE, so you look at the heat equation and another space-time white noise here, then this equation is well posed again with B is LQ integrable, and when B is bounded, then there is a result of Oleg and Leonid Minich, where they show further that the solution has a flow. The equation has a flow. So here the culture of probability is so the sub t here is not derivative, but just indication of time. Okay. So for fractional Brownian motion, so again we have an ODE, but then we add in a fractional Brownian motion. So you can think of fractional Brownian motion as fractional derivative or fractional integral of a Brownian motion. So it has a Hurst index h from 0 to 1. So if h is 1/2, then the fractional Brownian motion is the same as Brownian motion. So there's a recent results of Cartilio and Gubinelli. So they say that if B is a Bezout scale of beta, so any beta bigger than 1 minus over 2h, then there is a unique solution. So if h is 1/2, then so this is the case of Brownian motion, then any beta bigger than 0 is good. So namely Holder continuous of any order. if h is a quarter, then you get -1 here. So any beta became -1. So the fact that they find out is that the smaller the h, then the more irregular b can be. This is
Khoa mute unmute lại cái Khoa. Sorry.
okay. So okay, so the smaller the h, the better, the more irregular b can be. So it is known that fractional Brownian motion. So this guy is Honda continuous of any order a bit smaller than h. Okay, so you add in an irregular noise and the equation become better. Okay, so now I go back to my to the equation, which is again a stochastic equation, and so D can be either the interval 0, 1, and we look at Newman boundary condition or periodic condition, and D can be the full space. Then so if B is a function, you can write down the Maya formulation of the equation. So here this is just the heat semigroup, and then this is the heat density. And so here V is simply the convolution of the heat semigroup with the space-time white noise. So I miss the integration in space here. Okay, so but if when B is a distribution, we have to come up with another definition of a solution. So essentially just the Maya formulation, and we smooth out the distribution B and then remove the approximation by taking the limit in appropriate sense. So suitable smooth functions here essentially means that you take the distribution B convolution with a modifier, and then you remove the modifier. So any such approximation is suitable here. So I will not describe the detail of suitable. So the result that we have is, so the first one is the well-posedness results. So if this index beta minus 1 over p, which is also known as the Sobolev index, is bigger or equal to -1, and p is different from infinity, then there is a unique solution, and the solution is continuous with respect to the input, which is here the initial data and the drift. So if this index is bigger than -3/2, then there is a probabilistic weak solution. So I have some examples. So here the direct delta or any measures belong to this Besov scale, and for this class B0, 1, infinity, the index, the Sobolev index is 0 minus 1 over 1, which is exactly -1. So here we have a In our case, it will be critical because it is exactly -1. So other choices, so this is kind of a trivial choice. So B is u to the minus sigma. Sigma is between 0 and 1. And when sigma is exactly 1, then you have a Cauchy principal value, which is a distribution defined in this way. And this is a homogeneous distribution of order -1, and this also belongs to this kind of best of scale, the same scale as the beta, the same scale as the delta function. And of course, any LP will be embedded into this scalar best of space. So for all of these examples, we have uniqueness results. So the applications that we have is scaling limits. So here we take a drift, which is nice, regular, and integrable. And we look at the scale of these equations. So here we have a lambda -1 here, and we look at the limit of this solution where lambda goes to infinity. So so the result is if you look at the scaled equation, so where you scale time by lambda, you scale space by lambda square, and then multiply the whole thing with lambda to the -1/2. Then this random field converge in probability distributions to the skew stochastic equation. So here, so it converts to the solution of this equation with the delta, direct delta at 0, and then you have a constant in front, which is the total mass of the original function f. Okay. So if you take f that is not integrable, but only locally integrable, but under this kind of condition, so more or less, the function f is like a constant over x when x goes to infinity plus or minus infinity. Then you do the same scaling. We do the same scaling, and u lambda is as before, but now you have a conversion to the equation with the Cauchy principal value.
Hi, I have a question.
Okay, sure.
So in what sense are these converging? What is the sense of convergence? Is it convergence in probability or with convergence?
Convergence and distribution.
Okay.
So you take you look at this random field as a random variable on the space of continuous functions with respect to space and time. Then that random variable has a law, and then the law of that converts to the law of this kind of equation. Yeah, so I hope that answered the question.
Yes, thank you.
Yeah. Yeah, thanks for the question. So feel free to ask me questions if you want. Okay, so the well-posedness result is longer to explain, but then for the scaling limits, it's easier to explain. So let me try to do that. So essentially, there are just two steps. So the scaling steps, where we just rescale the equation, and we say that this one has the same probability law as the solution to this equation. And here f lambda is just the rescale of f, which is defined this way. So, and then we take the limit. So when lambda goes to infinity, f lambda will converge to the direct delta mass as distributions. And this is a known fact. But for f is locally integrable and satisfies some conditions, then the same guy will converge to the principal value distribution. And because we have shown that the equation is continuous with respect to the coefficients, and therefore when you have these convergence, you can just simply say that this equation will converge to the limiting equation. Okay. So let me tell you a bit more about the method.
Khoa, may I ask you
Yes.
a question? So
Yeah,
do you know whether the limiting equation has unique solution?
Yes, I'm sorry. I forgot to tell you that so the delta is so this guy is based off 0, 1, infinity, and the same for the principal value. The same for this guy. So we know that if it satisfies this condition,
okay,
which include the delta and the principal value,
okay,
then you have a unique solution.
okay, thank you.
And yeah, and essentially that is the part that the solution is continuous with respect to the input. So that's why we can just simply say that because the coefficients converge, then the solution converge. So let me tell you a bit more about the methods for these kind of problems. So usually the very popular method is the first one, the Zonkin transformation, also known as the Ito-Tanaka trick. So the idea is to use Ito calculus and rewrite the drift into other terms which have better regularity, and so this require knowledge, a very good background, very good knowledge of the PDE that associated to the SDE. But it only work when you have a Brownian noise, and in some cases space-time white noise also work, but very technical difficult. And another method is the nonlinear Young formulation that appear in Davy's work, but he didn't say it is nonlinear. But then later, Cattilia and Gupinelli reformulated into the language of nonlinear Young integral. So this method is only use martingale inequalities, sealing techniques, but it only works at the moment for additive noise, and it works for fractional Brownian motion and works for any other noises. So, so the method of the paper will is an extension of this method. So let me tell you. So about this method. So let's look at the Davy case. So Davy papers treat this SDE. So this is Brownian motion, and B is a bounded function. So Davy showed that for almost every sample path of the Brownian motion, then this equation has a unique solution. So his method is, so first you transform the equation, you look at the equation for the remainder, which is the difference of x and the noise. Then this psi satisfy this equation. And now the Brownian motion is inside the drift, and psi is the unknown. And he showed a kind of Lipschitz estimate for this time average integral. So it is Lipschitz with respect to x here. This is the variable. So even though the function b is bounded, you still have some kind of Lipschitz property. And based on this, he was able to show this results, that this equation has a unique solution for almost every sample path. And the method for the SPDE is similar. So we look at the transform equation. So this guy, psi, is the difference of u and v. Remember, v is the convolution of the heat kernel and the space-time white noise. So psi will satisfy this equation. And so we also have some Lipschitz estimate. So namely that when b is in this Berzov scale and with this kind of regularities restriction, then you have a Lipschitz estimate. So here kappa 1 and kappa 2 are some random fields. There's a condition that I didn't write down, that this guy has to be fs measurable, and this also fs measurable. So the restriction here is this one is strictly bigger than -1, and to cover the critical case when you have exactly -1, so we have to do something with you have similar estimate. It's just a log Lipschitz estimate, and log Lipschitz is good enough for uniqueness. Yes.
Sure. Well, can I have a question? So, I mean, it seems to me that you use the sort of the transformation c equals to u minus 3 very sort of effectively here. So, you know, if you have a little bit more complicated noise, then if you cannot do the transformation, then what happens?
So then, yeah, so no, the method doesn't work yet. But then there are a few cases that you can do multiplicative noise. So instead of Yeah, so instead of so you could have a sigma u here. Then this method doesn't work yet, but there could be some improvements to include a sigma, and this has not been done. For SDE, it has been done, but not at this level.
Thank you. That's really interesting. Thanks.
Yeah. So yeah. So to obtain this kind of estimate, so what we do here is we take a difference here, and then we take the LM norm, which is the moment norm, LM and omega. That is to use the stochastic sewing. So there are some exponents here that I won't be able to explain, but then let me just mention that. So a quarter is related to the regularity of the V. So it is known that this V is C 1/4 minus epsilon for any epsilon in time, and I have in space. Okay, so the 1/4 here is related to that guy, and then this exponent is simply the regularity here, the Sobolev index, -1, because you want a Lipschitz estimate here. So essentially, it's like we take the derivative of B, so we have less 1 regularity. And then the 1 here is coming out from the time integration. Okay, so let me explain to you the sewing method. So the general idea is you sum up local expansions to build or recover objects. So the trivial example that I like is the fundamental theorem of calculus, which say that for a nice function, you integrate the derivative, then you can recover the function. So what it means really is you take the Riemann sum of the left-hand side, which is f prime times the increment of time, sum up, and then take the mesh size, go to 0, then it converts to the increments of the function. So the connection between the Riemann sum in the right-hand side here is simply by this kind of approximation, which is just a linear approximation. So formally, if we replace this by the increments of from t to s, then after the sum, we get the increments. Okay, so that's the idea. So to formulate it, we look at the abstract Riemann sums. So here you have some kind of 2-parameter function AST, and we think of A ST as some local expansion around S. And the question here is under which condition you have a convergence of the Riemann sums. Okay, so very simple questions, but then come with the very big names. So, Lyons, this is the rough path paper. So he initiated rough path paper, and also Rubinelli. but the formulation with the abstract Riemann sum coming out from this paper. So it's a simple condition that you just compute this quantity, which is AST minus ASU minus AUT. So essentially, it's just the error when you split up the interval S to T, and we ask that this is a bit better than the linear one. Then the Riemann sum converge, and you can show some kind of continuity with respect to the germ. So A is a germ, and then curly A is the constructed process. So you can put some topology on it, and this will have continuity. Okay, so some examples. So the Young example. So here X is a whole continuous process. Alpha is bigger than a half, and F is very nice. And we want to understand this integral. So the setup is the A is just a local expansion here, which is F times the increments of X, and then this is the Riemann sums. And if we compute the delta A, then this is of order alpha, this is of order alpha. So we have 2 alpha. So 2 alpha bigger than 1, then the Riemann sum converge. So the rough integrals. So what happened when alpha is not bigger than a half, but then between 1/3 and 1/2? And we still want to build this guy. So we try the same strategy, but now it doesn't work because delta A is only of order 2 alpha. And if alpha is less than a half, then this is less than 1. Then it doesn't apply. So to overcome it, so they just, this is a magic trick. So we just assume that you are given a kind of, so you put more input into your hypothesis. So we are given the double iterated integral. And then in the local expansion, we add in a second order term. Now the abstract Riemann sum has this form. And then we go on and compute the delta A, which happen to have this form. So you see now that every term will have order 3 alpha. So this guy is of order 2 alpha. This is a Taylor expansion. This guy of order alpha, and this guy of order alpha. And this iterated integral is of order 2 alpha. So sum up to 3 alpha. So 3 alpha is bigger than 1, and you can use Sewing. So, and then you can go on, and if alpha is between 1/3 and 1/4, so then you need a 3rd order iterated integral. Okay. So this is a very rough idea of a rough path and also regulatory structure. And so if you look more into a subject, I suggest this book from Peter Frisch and Hira. Okay, so let's look at the Sewing lemma again. So the condition is that this is superlinear, 1 plus epsilon. But if we look at the Brownian motion case, and it is known that this integral exists because it is from Ito calculus. So the Ito showed that this Riemann sum converge in this in L2 sense. However, the condition doesn't satisfy because this is approximately exactly 1, and you don't have an epsilon there. So what happened? So it suggests that there should be some improvement, and this is the content of the stochastic sewing. So the stochastic sewing is only works when your process is in Lm omega, and m is at least 2. So the condition now is we measure delta A, and we ask that this is bigger than a half, and we measure the condition of delta A with respect to Fs, and we ask that this one is bigger than 1. Then you have convergence of Riemann sums. And there are other statements that you can characterize the resulting limit and also continuity with respect to the germ, so which I will not state. So let's look at the Ito integral. So now B is a Brownian motion, and F is C alpha. And then we take the same Riemann sum, but now so delta A is of order a bit better than a half. And then the condition of delta A, because of the property of the Brownian motion, this is 0, so this is 0. So you can apply stochastic sewing. Okay, so it gives you Ito integral, but not very optimal, because we know that if F is continuous, this is well defined, but here we need that F is order continuous. But nevertheless, we don't have to square the Riemann sums and compute. Okay, so let's see how it relates to the Davy estimate. So Davy estimate, I recall here, this is the Lipschitz estimate of this kind. So if we define this F, just simply divide by the difference of x1 and x2, then this F has a finite Besov norm -1 for this bounded B. Then Davy estimate is actually an estimate for the integral of a distribution B -1 composed with the Brownian motion. Okay, so now how do we estimate that? So I have a more general example. So this is so let's look at fraction of Brownian motion, and this is Besov on the scale, and we are interested in the regime when nu is negative. Okay, so this is a distribution, and we want to define this object so that it is a continuous extension of the usual integral, and we also want to study the continuity with respect to the input. Here's a time, the function f, and also some kind of perturbation. Okay. So the germ will be chosen to be the conditional expectation of the increments. So this guy we can compute precisely. So it's just simply the heat kernel applied to the distribution f and then evaluated at some random variables. And the sigma is has explicit form. So here I didn't write down. Oh, actually I have. So sigma is like a power to the 2h of time, and so to estimate a, we use just a trivial Schauder estimate or regularization of the heat kernel here. So namely, it maps hold the base of scale to bound the function, and you have a singularity of order nu over 2. Okay, so then after some computations, we can estimate this guy, and this is we ask that this is bigger than a half, and it turned out that nu has to be bigger than minus 1 over 2h. Then in this case, you can apply stochastic sealing to define this integral as the limit of this Riemann sum. Okay, so the trick is so this is ill-posed when f is a distribution, but then the Riemann sum doesn't care about that because of the convolution of the heat kernel and the f, and we have some estimates. Okay. So let me just mention that so when h is h is a half, right? So this is equal to minus 1 for h is a half. And this inequality is strict, so it doesn't really cover Davy estimates, because Davy estimates you want it to be exactly minus 1, but then again this method is generic and you can use it to other situations like fractional Brownian motion and SPDE. So okay, so I think that's the end of my talk. Thank you for your attention.
Có ai có câu hỏi hay có nhận xét gì không ạ? Cho Brownian motion part từ trước thôi, nhưng mà